Thank you so much. We are very, very happy to be here. A big thanks for everybody who is here attending our presentation, and of course, to the Nalcon team for making this possible. All right, let's get started. I guess we were already introduced. Maybe just a few words on what we are working on. So both of us are working on Android security, embedded device testing, as well as blockchain. So before I start the talk, I want to bring attention to kernel security and why is it important for all of us, not only for security researchers. The main reason is because critical Linux kernel vulnerabilities are happening. They are being published every once in a while. For example, there was one privilege escalation vulnerability in March this year, and also a critical remote takeover vulnerability in last November. So let's continue as an example with the second vulnerability, and let's ask a warm-up question, which is, how old is your smart TV? I'm asking this question because it is very much expected that if you buy a smart TV now, you might as well use it for 8 years, 10 years, or later on. But these smart TVs, after maybe 4 years, might not receive security updates anymore. And this is a problem to you, because then you're vulnerable to all the bugs that are reported after that and that are actually being researched on. So we have a case study here. This is the privilege escalation vulnerability that I mentioned in the previous slide, also known as dirty pipe. So it was only published in this March, but it's believed to be existing in the last 6 years. This is very similar to a CVE that was released in 2016. Now, what are the complications? The complications is that the patch to this vulnerability is only available to Linux kernel versions 5.16, 11, 5.15, 25, 5.10, 100.02. But there are many old systems that run on older kernels at the moment. Your smart TV might be one of them. And these are very vulnerable to this vulnerability, unless the device vendor is applying a manual patch by backporting. But this is often very cumbersome and it's not performed. So let's get started with our presentation now that you understand why you should care about the Linux kernel security. First of all, we will tell you a bit more about the problems in the Linux kernel patching. Then we will tell you what are the typical problems in kernel lifecycle management. Then finally, we will introduce Kernel Patchalyzer, which is a tool that we just released today for Nalcon. So we are really hoping that you will try our tool and give us feedback, and we will follow up with the details soon in this presentation. And finally, we will continue with the conclusion and the key takeaways. So let's get started. Kernel patching is a complex problem, and as you can see, there are many parties involved in it. For example, first of all, there is the Linux upstream kernel on kernel.org that every device kernel is based on. This doesn't have to be long-term supported, although we will explain why it is considered best practice. Then if you have an Android-based device, then you also have to import patches from the Android common kernel. And then, of course, your device runs on a chipset, and the kernel also has to be specific to the chipset that you're running on, that comes from the chipset vendor. And finally, you have your device kernel that is actually running the device. And here you have additional customizations, device drivers, etc. And basically, when you're patching your device, you have to consider all the patches from all these different repositories to make sure that your device is secure. So as you can see, there are multiple parties involved in kernel patching, and it also brings some kind of unique challenges. So as you can see, first, the patch is available in the Linux upstream or AOSP common repositories for Android. Then the chipset vendor also provides an update specific to the chipset. And then finally, as a device vendor, you update according to the drivers and your customization. And finally, you're ready to push out your security update, or your cellular operator as your client does it. But it brings some challenges. So for example, this is also something that we see during our security audits. But this is also something that people are researching. For example, there is a paper that we linked here from Zhang Zhen from last year, which basically found that many devices, for many patches, actually these patches don't reach the end-user devices when they are published, only a few months later, and this leaves the devices vulnerable to these bugs in the meantime. And another critical issue is that if you're a device kernel vendor, or if you're a cellular operator, or even an end user, you often don't know which patches should have been applied to your device, and you don't know whether these patches were actually applied. Just to be more specific and to show you what volume we are talking about, so this is statistics from the kernel vulnerabilities that were released in the first half of this year. As you can see, there are almost 130 of them, so quite a lot. And imagine that if you're a device vendor, you have to patch maybe all of them. And one other interesting factor is that 81 out of them are actually related to Qualcomm components, which are also handled by their own disclosure process, which means that the patching process is even more complicated than what we just talked about in the previous slide. And then I came to the most critical problem in kernel patching, which is fragmentation. By fragmentation, we mean that nearly all embedded devices have custom kernels. Why? Because you have a custom use case, custom hardware specification, and custom hardware drivers. And this is why security patches also require a lot of manual work. And each of the security patches need to be backported manually to the device kernel. That is a lot of work. And this is why also long-term supported updates from the mainline kernel is often really hard to merge. And sometimes it's also omitted when it's not possible for the device vendor. And from the opposite side as well, it's really hard to contribute custom changes back to upstream Linux. And as a result, a lot of kernels run on already, a lot of devices run on already older kernels that are at least 18 months old. Now, as a bit of a lookout, I can already tell you how we envision that automation can improve patching processes. So for example, if you're a maintainer, you want to make sure that you only apply the patches that are relevant to the device, so you don't waste your effort on patches that are actually not exploitable because you don't even have the components which are affected by the patch. And of course, you want to make sure that you applied all the security patches that are actually relevant to you. So basically, we have a couple of questions here that our tool logic is also following. The first is the vulnerability applicable to the used kernel version? Well, if yes, then is the component present in the kernel that is affected by the vulnerability? And finally, also very important, if this affected component is actually enabled in the kernel config, because if not, you don't need to spend effort on that. And also a very important question, whether the patch can be applied to said component. This is due to your customization. So it might be that you already completely changed the code in this component that you enabled. You might need to think of a custom patch solution, or you decide that you're not vulnerable to this. But this usually involves a manual process, regardless of automation or not. And finally, of course, you want to know whether all the applicable patches were applied or not. So let's continue on the kernel lifecycle management. First of all, I want to talk about the main problems of device vendors. So we identified 4 critical areas. The first one is determining the life cycle and the support timeframe for security patches. The second is some legal requirements. The third one, which is crucial, choosing a Linux kernel version that supports the maintenance plan that you have. And finally, you also have to align the kernel version and support file timeframe with your chipset vendor. And of course, you cannot just choose any chipset vendor because this is highly dependent on your device's hardware specs. So let's jump into the first topic. So as I already mentioned, many embedded devices have a way longer expected life than smartphones, which is generally set to 2 to 4. But for example, if you have a smart TV, you have maybe 10 years, maybe 15. Or if you have a car, at least 15 years. So device vendors have to juggle a lot of different requirements and also some problems when they want to set a support time frame. First of all, as we mentioned, there are legal requirements for patching. There are client expectations for patching, especially by cellular operators. There is fragmentation. As a device vendor, you don't have only one device, but you have probably hundreds of different devices. And you need to support them with security updates for many years, and not just one, but all of them. And then there are also problems when a kernel version is fixed by a chipset vendor and maybe run out of support during the device's lifetime. And in this case, you also have to continue supporting it with a higher effort. And then a short consideration on the legal requirements. This is relatively new. For example, I'm bringing Europe as an example because we come from Germany. There was an EU legislation in 2019 which made it mandatory for the device testers, device vendors, basically 2 things. First of all, vendors need to ensure that end users are aware of the support time frame and also the security update schedule. And the second point is that each device must be given a security update in accordance with the expected lifetime, which may or may not be happening at the moment. And just to show you how recent is this, countries are also very slow to adapt to these rules. For example, for Germany, it took 3 years to start enforcing this, which means that basically they made it effective in this year. So now I'm giving the word to Jakob, who will continue explaining why is it important to choose the kernel version, right?
So from the point of view of a device vendor, the first step in patching a device is to decide which kernel version you are using. And it is always preferable to use an LTS version. It is always preferable to get an LTS version, which will get a couple of years of security support from upstream, so from the upstream Linux kernel repositories, or from the Google AOSP repositories if it is an Android-based device. And in some cases, it may also be necessary to do a major version upgrade of a kernel within the lifetime of a device in order to fulfill the lifetime requirements for patching. And what should in any case be avoided is using an unsupported kernel version, so one kernel version which is not an LTS version and will be out of support pretty soon. So this should be avoided because it is very hard to backport all pending security patches to a non-supported kernel version, especially since many patches are just not available for that kernel version and needs manual backporting. So let's look at the options we have as a device vendor. From the upstream Linux kernel developers, we have several LTS versions. We have currently supported version 4.9, 4.19, 5.4, and 5.10. And we can see the lifetime of this version. So the latest version you can get at the moment will be supported just until December 2026. So this may not be long enough for your device, especially if you're building something like a smart TV or even automotive components, which may be in operation during the lifetime of a car. And apart from the Linux upstream kernel, we also have the Android common kernel. And for Android, Google has a policy that one given Android version supports the 3 latest kernel versions supported by AOSP. So there is an option to upgrade the Android operating system without upgrading the kernel. But still, after a couple of upgrades, you also need to upgrade the kernel. And lately, Google is making efforts to improve the situation by forcing vendors to support a generic kernel image. So you have one generic kernel image coming from Google, and it will load some custom modules from the system on chip vendor or from the device vendor, but the main kernel is coming from Google and can be upgraded by Google. So let's look at the situation if we can't find a kernel version which is supported for the full lifetime of a device. In that case, you will have to upgrade to a newer version during the lifetime of a device. And this is very hard to do without support of the chipset vendor. So in some cases, it is possible to do that without explicit support from the chipset vendor, but in many cases, it is also completely impossible. For example, if the kernel provided by the chipset vendor contains some closed source components or binary blobs, which only support one specific kernel version, and if a chipset vendor is not willing to upgrade that, there's little you can do to still support that device. And unfortunately, chipset vendors are sometimes reluctant to provide security upgrades for older chipsets, which are already out of mass production and don't bring them any more money. And due to these complications, in many cases, a major kernel version upgrade is not performed, and this makes it effectively impossible to actually apply all security upgrades to devices. And this is one of the reasons why many devices in use today do not have all security upgrades which should be applied. So let's talk a bit more about the effort required for patching unsupported kernel versions. So you have some upgrades from some security patches from upstream Linux. You may have some Android-specific security upgrades from Google. You have some security upgrades for chipset-specific components from your chipset vendor. And you may also have some device-specific drivers for your device. And all of these components may have security vulnerabilities and may need patching. And you have to backport all the patches to your device. And backporting patches can be a very complex process because it needs a lot of understanding of the vulnerability and also understanding of the component being patched. So So the best way to deal with this is to talk to your chipset vendor at the time you're designing your device and choosing a chipset. And you should, first of all, clarify the requirements you have. So, for example, the requirement could be patching for 5 years and running a supported Linux kernel version for 5 years. And this may lead to a situation where you have to upgrade to a newer LTS kernel version during the lifetime of the device, and you should agree on that with the chipset vendor, so that the chipset vendor is responsible for actually providing an upgrade to a new LTS kernel version. And in some cases, the chipset vendor may not agree to that, and this means that the chipset does not fulfill your requirements. So the security patching is pretty much as important as the hardware specifications of a chipset, and you may be in a situation where you have to choose a different chipset to reach the required level of security patching. And as a last resort, you can also backport patches without support for a chipset vendor, but this should be avoided if that is at all possible. So let's talk about what we are doing to improve the situation. We have implemented some automatic analysis tool called Kernel Patchalyzer, and it allows analyzing one kernel source code tree and see which patches have been applied and which patches may have been missed. And there are two different positions how you can look at this problem. One is the position of the device auditor, that is, for example, us. So we are often getting a task to review the security of an embedded device or an Android-based device for a customer. So in many cases, the customer are telco operators, which are buying devices from third-party vendors and want to make sure the devices reach the security requirements. But also some device vendors also ask us to test the security of their devices. And so we are getting a lot of kernels, source code trees, and we have to check if they are actually patched or not. And it was quickly clear to us that doing this manually for a large number of devices is not practical. And so we had to write some automation to deal with this problem and automatically analyze the patch status. But you can also view out the problem from the side of the device vendor. So as a device vendor, you may have a large number of different devices to support. The devices may be running different kernel versions, and you may have a lot of kernel developers in your team, and it is very hard to confirm or verify that all of the patches that should have been applied have actually been applied. And our tool can also help the device vendors to find gaps in their patching process and improve the situation for their devices. So let's take a look at how we are doing it. First of all, we need to find a database of security vulnerabilities and patch commits. So for each security vulnerability, we collect one or several Git commits which are patching the vulnerability, and we are finding that from public Git repositories from a couple of different sources. And then we run our analysis logic to find out whether the patch is applied or not. So the easiest way to check if a patch is applied or not is to try if you can apply the patch. If you can apply the patch and you cannot revert the patch, you can be pretty sure that the patch is missing. But if you can revert the patch and you can't apply the patch, you know that the patch is already applied and everything is fine. And additionally to that, we have an optional step to instrument the build system so that we find out which parts of the kernel, which files in the kernel source code tree are actually compiled for a given device for a given kernel configuration. And this allows us to ignore patches which are just not relevant to the device because their patched files are not compiled into the kernel. And we have also spent a lot of time in optimizing the process so that the analysis is running fast, and now we have reached a point where we can run an analysis in less than 1 minute for hundreds of CVEs. So first of all, let's take a look at the process of finding the different CVEs. So first of all, we have to find the vulnerabilities. The main source of it is the Android Security Bulletin, which is released every month by Google. And it typically contains a number of kernel patches. And from there on, we can try to find commits for the vulnerability. So commits patching the vulnerability. And for each commit, we look into the Git repository and check out the make file and get the kernel version, because we need to know which patch is for which kernel version, so that if we have several patches for the same vulnerability, we can choose the closest matching kernel version. And When we also look for all commits in different Git repositories from different sources, such as the upstream Git from Linux, the Google Android Git repositories, and also some repositories from Qualcomm Code Aurora for Qualcomm-specific patches. And we look for the commits, we match the commits with vulnerabilities based on information in the commit. So sometimes we find a CVE ID in the Git commit message. Quite more often we find an Android bug ID, which can be correlated with the CVE via the Android security bulletin, and we find that in the Git commit message. Or for Qualcomm-specific patches, we find a QCCR identifier, a Qualcomm change request in the commit message. And once we have found one commit for it, we often find a change ID, and if we find a different commit with the same change ID, this pretty much always means that the commit contains the same change set, just for a slightly different kernel version or branch. So we can use that information to collect which commits are for which vulnerabilities, and then we can use these commits for testing if the patch is applied or not. So let's take a look at it. We first try if the patch can be applied to the source code tree via testing, and then we also try if the patch can be reverted. In some very rare cases, the same patch can be applied, but it can also be reverted. That is typically because the file contains similar sections with the same context lines, and then the patch testing is not very reliable, so we can't really tell whether the patch is applied or not in an automated way. But in most cases, we have a clear indication based on this test if the patch can be applied or reverted. And also in some cases, we have a situation where the patch cannot be applied and it cannot be reverted. And in that case, we are using a second analysis step. So we are looking at the Git history of the files being patched. And we are using the Git blob hash, so basically a hash of a file we are testing, and see if we find it anywhere in the Git history before or after the patch. And if we had some other changes in between, which make it impossible to apply the patch or revert the patch directly, we can still say that this patch matches the version long after the patch has been applied, and in that case we know it is patched. Or if the file matches a version long before the patch was applied, we know the patch is not applied to this kernel. So this is the main steps, how we are testing whether one patch is applied or not. And in order to do this analysis in an efficient way, we also have spent quite some time in optimizing the process. So we have introduced some database-based caching. So for example, for a Git repository, it is pretty easy to traverse it from one commit to the parent commits and then to the further parent commits and so on. But it is very hard to traverse it in the other direction, so to find all commits based on one given commit, because the Git data structures are just not made for that. And so we implemented some database-based caching using MySQL to speed up this process. And we also cache some results of the apply and reversion tests. And we also use some pre-computation. So if we look up the file git blob hash, we have to calculate the git blob hash of a file. And in many cases, we end up needing the same blob hash for the same file multiple times for different CVEs being tested. And so we pre-compute it. So in the beginning of analysis, we are calculating the hash of every file and then caching that, so we don't have to repeat it over and over again for the same file. And last but not least, we are parallelizing the process using the Python multiprocessing module, which is the most efficient way to parallelize Python programs efficiently. And we are doing it by testing different CVEs on different worker processes, and this provides sufficient parallelization since we typically have hundreds of CVEs to be tested, and we normally use something like 32 worker processes on a large machine. So having more than 32 worker processes doesn't actually speed it up anymore because of some overhead. So by default, we're using the number of CPU cores available, but with a maximum of 32. And once we have done the analysis, we can also do some further testing for false positives. So we have implemented the build system by introducing some warning directives into every single file being compiled, so into C files, into assembly files, and into header files. And then after introducing these warning messages, we are running the build system and collecting the build log, which contains thousands of warning messages. And then we can correlate these warning messages with the files. And all the files being used by the build system can be collected, and then we can explicitly exclude patches which only patch files which are not even built for this device. And this helps us filtering out some false positives. And additionally to that, we also use the architecture. So we have quite a lot of patches which only affect specific architectures or chipset vendors. So for example, we have patches specific for Qualcomm. There's no need to test that when analyzing a MediaTek kernel, or we have patches which affect x86 only. There's no need to test that when analyzing the kernel for an ARM by smartphone. So we can filter out quite some false positives for patches which are technically speaking not applied, but which just don't matter for the device being tested, so it is not strictly necessary to apply these patches. And we have an announcement. We have released it publicly today. It is available on Docker Hub. You can find the URL here. And we will also push it out on GitHub very soon with the build instrumentation feature I've just talked about. So you can now start using our tool via Docker and analyzing your own kernel, whether you are a device vendor or a security tester for embedded devices. It is now very easy to just run with logic and test a kernel source code tree for missed patches and improve the patching status. So let's come to our demo. So Regina is now running the demo. We are pulling it from Docker Hub. It will normally take quite a bit more time because it is something like 10 or 15 gigabytes to download, but we have already downloaded it before the demo to speed up the process. And now we are starting the analysis. So it is just one single Docker run command. We need one volume parameter, one shared folder, which is shared between the host system and the Docker container. It's the current working directory. And when we specify that there's the root parameter for the Android kernel source code tree to be tested. You have to move it to the other screen. We have the presenter mode. We have the presenter mode on. Can you move it to the other screen or mirror screen?
Can you disable that? Now we can see.
Yeah, so sorry for the issue. So we have already put, we are just starting from the beginning. So the first step is to pull the image from Docker Hub. So when you are doing it, it will take some more time because you have to download something like 10 or 15 gigabytes. And then the next step is to run the analysis. So here's you see the command. You need a shared directory with the -v parameter of Docker. And when the kernel needs to be tested, needs to be below that directory. You have to specify a name, which will then be a part of the analysis results. And you also need the architecture. In that case, we are testing a recent kernel from the Google Android kernel, and for the architecture ARM64, which is used by modern smartphones. And you also need to specify the output directory. The analysis will in the end show and write one Excel file with the results and also one JSON file if you want to analyze it manually or write your own tools based on that. So now the analysis is running. It will load some data, and then it will take a couple of seconds when it pre-computes the blob hashes from the files being tested. Now it starts the worker processes and actually testing the CVEs to be tested, and it will take about half a minute until we have the results. Okay, now we have saved the results, and Regina will now open the Excel sheet generated with it. So here we see this. Yes, we see the patches. Most of the older patches from a couple of years ago are just not affected because we have a pretty recent kernel, and if a vulnerability is already patched in the base kernel release for a kernel version, then there's no need to test it in any kernels based on that, so it is not affected. And then when scrolling down to the more recent vulnerabilities, we see a couple of cases where the test failed because our analysis logic is not perfect. But it also shows many cases where the patch has indeed been applied. And as expected for a recent Google kernel, all the patches have been applied. And this is quite expected because Google is very good at patching their Android kernel source code trace.
All right, then I hope you will get the chance to try it on your own, and feedback is very much welcome. So let us know how you like it. If you have any problems, we will try to solve that. And now I would like to conclude the presentation with some key takeaways. So first of all, we discussed automation a lot. And of course it's great, and we believe this will really help the ecosystem, but it has its limitations, and it doesn't solve all the problems in the Linux kernel ecosystem. For example, it doesn't solve fragmentation. I already mentioned that many device vendors have a lot of devices that they need to maintain, and in these cases they might just prioritize the higher-end devices that they sell for a higher price while neglecting the lower-end devices, unfortunately. It will also not resolve the security support for certain cases because right now it's still very much not mandated and often too short compared to the actual time of life of the device. But we believe that it can solve other parts of the development process, and we have a few suggestions. So first of all, automation could be used to improve the patching process during development. And this flowchart that you see here is exactly the same questions that we asked earlier during the presentation. And basically, kernel developers, while patching in the next, to meet the next security update deadline, they could use our tool to ensure that they applied all the patches. Now, Jakob mentioned that kernel patchalyzer automatically applies patches as part of the analysis. So, in theory, this could be also enhanced to actually start patching in an automated way. However, we personally did not test it and we did not further investigate it, but this is a subject for future research that we might want to explore. Secondly, it might be useful as a sanity check for device vendors. So after you prepare the security update that you want to push out, you could basically execute kernel patchalyzer to find out whether there were any CVEs that you missed that you still need to patch. And we have a side note here. The Linux kernel has a GPL license, which basically requires device vendors to disclose the kernel source code publicly. However, we saw it during our auditing of embedded devices, and also we know from cellular operators that this is not often the case, and device vendors simply fail to comply with this and do not disclose the kernel source code. However, if the device vendors themselves have this tool, which is now available, they can themselves perform a sanity check or as an internal verification, which might help ensuring the security of the ecosystem. And finally, as I already mentioned, verification is increasingly important as it's necessary to ensure security. And as a security company, we are doing that for partners. We are running kernel patchalyzer in our device testing assessments. And of course, for the end users and for the operators, external verification is great, but also internal verification by device test vendors is already improving the current situation. So this was the closing part of my presentation with an optimistic note. I hope you enjoyed it, and if you have any questions, please let us know.
Do we have any questions? Thanks a lot for your talk. I have several questions. First, Linus Torvalds and Greg Hartman say that there are no vulnerabilities and all fixes are just maybe security fixes. So they recommend follow the stable tree and and vendors should take all the patches from stable. And is it possible or applicable to your tool to follow all the stable patches which are coming? Because maybe there are some fixes which didn't get CVE, but they are security issues.
At the moment, we are only testing vulnerabilities which have been published, which have a CVE ID. But of course, the same analysis logic could be adapted to be used for all patches applied to one of the LTS kernel versions by the upstream Linux kernel.
Okay, thanks. And another question. I know some vendors, especially for Android phones, they don't provide the Git repository of the kernel. They just give it archive with all the source code and so on. So the idea of trying to apply and revert patch doesn't work for that, right?
Yes, it works for that, and the automated tool will not even check for the Git history, even if it is available.
Okay, and I have a friend, Denis Yefremov. His project is CVE Hound. It is the project which tests Linux kernel for vulnerability fixes, and it uses the Kernel semantic checker. It is like the tool for creating automatic patches for Linux kernel and so on. So he writes the descriptions of the fixes of vulnerabilities in this semantic grep and just searches for that. Maybe it is an idea for you, not just test patches, but somehow semantic search the source code of the Linux kernel for the fix of the vulnerability. Yep.
We haven't looked into the semantic search so far. Until now, we have just used the patches available to it or not.
Thank you very much. Thanks for the talk.
Anyone else? Any questions?
Hi, great presentation. Thanks for this. My question was that from the command line, where do you mention that which SOC vendor it is actually? Like, where do you get all the patches from specific to the device?
You get that? Sorry, can you repeat the question?
So basically, if a chipset is from Qualcomm, they need to comply with the Qualcomm patches. Where do you mention that in your tool? Like, you need to get the Qualcomm patches as well, right?
So when we test for a Qualcomm specific patch, we don't really specify it within the tool, but if you see which CVEs are tested for, you can then search for them and see whether this is a Qualcomm specific patch or other chipset vendor or it is generic kernel.
Okay, thank you.
Anyone else?
Okay, last call for any questions. Thank you.
All right, thanks again.